Okay, so new definition. An eigenvector of an n by n matrix is a non-zero vector, which we will call X, such that A times X is equal to lambda times X for some scalar lambda. And so a scalar lambda is an eigenvalue of the matrix A if there is a non-trivial solution X to the equation A times X is equal to lambda X. By non-trivial, we mean a non-zero vector. And such a vector, X, is the eigenvector corresponding to the eigenvalue lambda. So an eigenvector of a square matrix is a special vector such that when the matrix A transforms that vector, the result is a scalar multiple of that vector. So depending on the scalar, this could be a contraction, a dilation, or even changing the direction of the original vector. But in all cases, when the matrix A acts on this vector, the result is a vector that is on the same line as the original vector. So notice that if AX is equal to lambda X, then we can rewrite the right-hand side to be lambda times the identity matrix times the vector X. And then we have that A times X minus lambda I times X is the zero vector, or the matrix A minus lambda I times the vector X is the zero vector. Okay, so new definition. Let A be a n by n matrix. Then the determinant of A minus lambda I is a polynomial in the indeterminate lambda, or the variable lambda, of degree n. And that polynomial is called the characteristic polynomial of the matrix A. And the equation the determinant of A minus lambda I is equal to 0 is the characteristic equation. Of the matrix A. So notice that the scalar lambda is an eigenvalue of the matrix A if and only if that scalar lambda satisfies the characteristic equation. Which again is the determinant of A minus lambda I is equal to 0. So new definition. A triangular matrix is an n by n matrix with all zeros either above or below the main diagonal. And triangular matrices are nice because it is easy to determine the eigenvalues for a triangular matrix. So as a theorem, let A be a triangular matrix then the eigenvalues of A are the elements on the main diagonal. So proof. We're going to prove the 3 by 3 case. Since for our applications to geometry, we're only going to be working with 3 by 3 or 2 by 2 matrices. So let A be the square matrix with first row A11, A12, A13, second row 0, A22, A23, and third row 0, 0, A3, 3. So this is a triangular matrix with all zeros below the main diagonal, and we call this an upper triangular matrix. So if A is that upper triangular matrix, then the matrix A minus lambda I is the square matrix A11 minus lambda, A12, A13, 0, A22 minus lambda, A23, 0, 0, A33 minus lambda. So the characteristic equation is 0 is equal to the determinant of A minus lambda I. So to take the determinant of a 3 by 3 matrix, we can use the cofactor and minor expansion, and we can choose to expand about the third row because we have two nice zeros to work with. And so this determinant is the quantity A33 minus lambda times the determinant of the 2 by 2 matrix A11 minus lambda A12 and 0 A22 minus lambda. And so this is the quantity A33 minus lambda times the quantity A11 minus lambda times A22 minus lambda minus 0. And so this is the product of the quantity A11 minus lambda times A22 minus lambda times A33 minus lambda once we rearrange. And remember that lambda is a eigenvalue if it satisfies the characteristic equation, and hence the eigenvalues of the matrix A are A11, A22, and A33. That is the elements on the main diagonal of the matrix A. Okay, so we looked at an upper triangular matrix. Let's now look at a lower triangular matrix to make sure that there's nothing special about an upper triangular matrix. So let A be the square matrix with first row A11, 0, 0, A21, A22, 0, and A31, A32, and A33. So here all the zeros are above the main diagonal, and so we call this a lower triangular matrix. And for this lower triangular matrix A, we have that A minus lambda I is the triangular matrix A11 minus lambda 0, 0, A21, A22 minus lambda 0, A31, A32, and A33 minus lambda. And so the characteristic equation is 0 is equal to the determinant of A minus lambda I. And again, to take the determinant of a 3 by 3 matrix, we can use the cofactor and minor expansion. And in this case, we'll choose to expand about the column, the third column, since we have two zeros to play with. And so this gives us the quantity A33 minus lambda times the remaining determinant of the 2 by 2 matrix, A11 minus lambda 0, A21, and A22 minus lambda. So we have A33 minus lambda, the quantity A33 minus lambda, times the quantity A11 minus lambda times A22 minus lambda, minus 0. And so this is the product of the quantity A11 minus lambda times A22 minus lambda times A33 minus lambda once we rearrange the terms. And hence, the eigenvalues of the matrix A are A11, A22, and A33, which once again, the elements on the main diagonal. On the matrix A. Therefore, we can conclude that the eigenvalues of a triangular matrix are the elements on the main diagonal. Of the matrix A, at least for the 3x3 case and below.